Have you ever looked up at a star, really looked, and wondered what's actually going on inside? They look so simple, right? Just points of light. But underneath, there's this incredible complexity, often real chaos. And understanding those churning interiors, well, it's key to unlocking some really big cosmic secrets. Today, we're diving deep into one of the most fascinating but also notoriously difficult processes inside stars, stellar convection.
That's right. And our mission today, essentially, is to unpack why convection is just so vital for how stars actually live their lives and evolve. We'll dig into the main way scientists try to get a handle on it, this thing called the mixing length theory. Then we'll look at the challenges, the persistent problems with it, and finally explore how amazing new data, especially from missions like Gaia, is really shaking things up and refining our understanding.
Okay, and guiding us through all this stellar physics is some fantastic material, particularly a recent essay by Michael Perryman and the research he draws on. So let's get right into it. What is convection fundamentally inside a star? Why is it so important?
Okay, so at its most basic, convection is just a way energy moves around. Think of like a pot of boiling water, but scaled up astronomically. Hotter stuff rises, cools off, sinks back down, this constant circulation. Inside a star, the actual size of that boiling region, the convective core, well, we can probe that using something called astroseismology, basically listening to starquakes. And the size of that core, it's crucial, especially for stars a bit heftier than the sun. It tells you how much nuclear fuel the star can actually use. That directly sets its brightness, its luminosity, and ultimately its total lifespan.
Astroseismology, listening to stars, that's amazing.
It really is. And there's another layer too, something called overshooting. That's where the convection currents kind of slosh beyond their expected boundaries. It seems subtle, but it actually modifies our standard evolutionary models for stars, say, above 1.2 times the sun's mass. Changes their predicted lifetimes.
So it's not just the boiling in one zone, the effects spill over. Are there other ways things get mixed up inside?
Oh, absolutely. Convection isn't the only game in town, especially in what we call the radiative zones. In those regions, energy travels mostly as light, photons bouncing around, not material churning. But even there, you get mixing. There's microscopic diffusion. Gravity slowly pulls heavier elements like helium down towards the center. But then you have turbulent mixing, often stirred up by the star's spin, its rotation. And that can actually fight against the settling, making things, well, even more complicated.
Okay, wow, it sounds incredibly dynamic. A
Yeah.
real 3D chaotic dance inside. So how on earth do we model that? Especially if, as you mentioned, it's often simplified.
Yeah, you've nailed the core problem right there. It is this complex 3D physical process, but building full 3D models for every star for its entire life, computationally, that's just immense, often impractical for large-scale studies. So for practical reasons, most stellar evolution codes simplify it. They treat it as a one-dimensional flow, basically averaging things out radially.
A 1D description for a 3D reality. That sounds like a big source of uncertainty.
It absolutely is. In fact, convection represents one of the biggest sources of uncertainty in our current stellar models, and the consequences are huge. This simplification, this uncertainty, it translates directly into major question marks over stellar ages. We're talking potentially billions of years. And if you don't know star ages accurately, that really messes with your understanding of how galaxies built up their chemical elements, their merger histories.
Everything.
Billions of years.
Yeah.
Just from simplifying the internal boiling. That's quite something. So the simplification leads us to the main tool scientists use, right? The mixing length theory, or MLT.
Exactly. MLT has been the workhorse for decades. Its origins go way back to 1958 to Bum Vitens's work looking specifically at convection in our own sun.
Okay, so how does it work? How does it try to capture that churning motion? Well, it uses this analogy. Imagine a blob, a parcel of hot gas inside the convection zone. It rises, holds onto its heat and identity for a bit, travels a certain distance, and then mixes with its surroundings, giving up its extra heat. That characteristic distance it travels before mixing, that's the mixing length. It's usually thought of as the average distance the parcel can go, and it's measured relative to something called the pressure scale height.
The pressure scale height.
Wait,
What's that roughly?
it's basically a measure of how quickly the pressure inside the star drops as you move outwards. A characteristic length scale defined by the star's structure. So the mixing length is some fraction of that scale height.
Okay, I think I can picture that. A rising blob travels a certain distance, mixes. But, given it's from 1958, why is this relatively simple picture still so dominant with all the computing power we have now?
That's a really good question. Its persistence, I think, tells you two things. One, it's actually surprisingly robust and useful. It captures some essential physics, despite the simplification. But two, it also underlines just how incredibly hard it is to build a significantly better, yet still computationally tractable alternative for general use.
So the full 3D simulations, they exist, but they're not easy to just plug into models of whole star population.
Precisely. We can do detailed 3D simulations, especially for the sun, and they are very successful. They reproduce what we see, the granulation patterns, the spectra, the results from helioseismology, the sun's vibrations. But applying that level of detail consistently across all types of stars, all stages of evolution, that's the bottleneck. MLT offers a workable shortcut.
A shortcut with limitations, though.
Definitely. It works reasonably well for stars like the sun on the lower main sequence. Their radii aren't super sensitive to the details of convection, so tuning MLT based on the sun gets you pretty close. But for stars much more massive than the sun, or stars that have evolved off the main sequence, like giants, MLT's predictive power becomes much more limited.
Okay, here's where it gets really interesting, I think. You mentioned the mixing length is some fraction of the pressure scale height.
Right.
This brings us to a really critical number, right? The mixing length parameter, alpha ml. What exactly is that?
Right, ML, or alpha ML. It's basically that fraction we just talked about. It's a dimensionless number, just a pure number that quantifies how far that convective parcel travels, measured in units of the pressure scale height. You can also think of it as tuning the efficiency of convection. A larger alpha ML means convection is more efficient at carrying heat outwards.
And this single number, it has big consequences for stellar evolution.
Huge consequences, especially for stars that have convection zones near their surface, which includes stars less massive than about 1.2 times the sun. Changing the value you assume for alpha ML directly changes the model star's internal temperature gradient. That, in turn, affects how fast nuclear reactions happen in the core. And that ultimately changes the star's main sequence lifetime, how long it spends burning hydrogen. So yeah, a different alpha ML can lead to a very different age estimate.
So let's bring this home for the listener. Why should you care about this specific parameter, alpha ml? What's the big deal?
Well, the big deal is that stellar ages underpin so much of astrophysics. Want to understand how planetary systems form and evolve around other stars? You need the star's age. Want to trace how galaxies like our Milky Way built up over cosmic time, their chemical enrichment when different parts formed, when mergers happened? You need reliable stellar ages. Even dating ancient star clusters, globular clusters, it all relies on accurate stellar models. And get this, if you're trying to figure out the age of a red giant star, just choosing a different plausible value for alpha ML can change your age estimate by several billion years.
Several billion. That's enormous.
It really is. It directly impacts things like mapping the Milky Way's age-metallicity relation, how the chemical composition of stars relates to their age, which tells us about the galaxy's history. Some recent work, Wang and colleagues in 2023, looked at red giants. They found typical age uncertainties around 30% just from this kind of modeling issue. And improving how we handle alpha ML is key to shrinking those error bars.
Okay, 30% uncertainty is massive when you're talking billions of years. But thankfully, we're not just stuck with theory. We have incredible new observations coming in, right? Especially from the Gaia mission.
Yes. Gaia is a total game changer here. Its ability to measure distances and therefore intrinsic luminosities with unprecedented accuracy for millions, even billions of stars. It's phenomenal. For red giants, for instance, Gaia gives us precise luminosities across a huge range of metallicities and ages. This is forcing us to revisit alpha ML. We need better ways to characterize it, understand how it might depend on a star's temperature, its surface gravity, its chemical composition. Gaia's data is the benchmark we need.
Can you give a specific example of how Gaia is putting these models to the test?
Sure. There's some great work by Brandner and collaborators using Gaia data, specifically the EDR3 release. They looked at single stars in the Hyades cluster. The Hyades is fantastic for this because its stars form together, so they should trace out a really tight sequence in brightness and temperature, the main sequence. This makes it a perfect laboratory for testing theoretical evolutionary tracks, like those produced by the popular MESA stellar evolution code.
Okay, so they compared the precise Gaia data for Hyades stars with the MESA models. What did they find? Did the models hold up?
Well, it was mixed and really interesting. The standard MESA models, the ones that don't include stellar rotation, they actually fit pretty well for stars more massive than about 0.85 times the sun's mass. And they also worked well for the very tiniest stars, below about 0.25 solar masses. But for the stars in between, those intermediate mass K and M dwarfs, the models systematically underestimated the observed luminosity. The real stars were brighter than the models predicted.
Underestimated luminosity. What does that imply? What could be going wrong in the models?
One strong possibility, especially for the stars above, say, 0.35 solar masses, is that the models are using an alpha ML value that was tuned specifically to match our sun. But maybe that solar tune value isn't quite right for these less massive stars. If you apply a solar calibrated model to these lower mass stars, the mismatch suggests you might be seriously underestimating their true age or maybe overestimating how metal rich they are. Both have big implications.
So the sun isn't necessarily the template for all stars when it comes to convection.
It seems not, or at least the efficiency might vary.
And you mentioned something about the very lowest mass stars, too. Below 0.35 solar masses, something about
Yeah.
kissing.
Ah, yes. The convective kissing instability. It's a fascinating process predicted for these very low mass stars. What happens is they burn helium-3, but not quite in equilibrium. This can cause the small convective core to actually grow until it expands outwards and touches or kisses the deep convective envelope reaching down from the surface. When they touch, the star can temporarily become fully convective mixing from center to surface. This triggers these little episodes, causing small changes, maybe a few percent in the star's radius and luminosity over really long timescales, millions to billions of years. It's another complexity Gaia might help us spot.
Wow, convective kissing instability. The universe is endlessly creative. So MLT is the main player, but we know it has issues. Are people developing completely different approaches? You mentioned alternatives earlier.
Yes, there are some. The codes like ATON and CSAM, for instance, use a different theoretical framework, sometimes called a full spectrum turbulence model. These are physically more sophisticated in some ways. But again, the fact that MLT, despite its known flaws and its age, remains so widely used in major stellar evolution codes, it really just hammers home how difficult this problem is. Creating something fundamentally better that's also robust and computationally efficient for modeling huge numbers of stars is a massive challenge.
Okay, so let's zoom out again. We've seen how convection and this alpha ML parameter affect individual star ages, galaxy histories. Does it connect to even bigger cosmological questions?
It absolutely does. Think about how we measure the scale of the universe itself, the cosmic distance ladder. One of the most crucial rungs on that ladder relies on Cepheid variable stars. Their pulsation periods are linked to their intrinsic brightness, but modeling Cepheids accurately also involves convection, and therefore Alpha ML, work by DeSoma and others in 2022, looked directly at this. They checked how different values of alpha ML affect the predicted relationships for Cephides, and they found that a specific value, alpha ML around 1.7, used alongside the standard mass-luminosity relation for Cephides, gives results most consistent with the Hubble constant, the universe's expansion rate measured by recent colleagues using Cephides and supernovae.
So a detail about how gas churns inside a star helps calibrate the expansion of the entire universe. That is just mind-blowing.
It really connects the microscopic physics inside stars to the largest scales imaginable.
What an incredible journey today. Seriously. From the turbulent, boiling interiors of stars, we've seen how this one parameter, alpha ML, the mixing length, can ripple outwards, affecting our estimates of stellar ages by potentially billions of years, reshaping our understanding of galaxy evolution, and even fine-tuning our measurement of the universe's expansion. It's like this hidden dial controlling cosmic clocks.
It's a fantastic illustration, isn't it? Even in areas we think we understand reasonably well, like basic stellar structure, fundamental processes like convection still harbor significant uncertainties. And it shows why new, ultra-precise data like what Gaia is providing is just so crucial. It constantly forces us to confront our assumptions and pushes us towards a deeper, more accurate picture of the cosmos.
Absolutely. And it leaves you wondering, doesn't it?
That's her.
Given how much this one parameter, alpha ML, can shift our view of stellar ages and cosmic history, what other seemingly small details, hidden assumptions within our models might be quietly rewriting the story of the universe right under our noses? Something to think about.